Okay, I think we'll get started. So today we're talking about friction and drag. If you're coming from the GNL project, I encourage you to look at the introductory video for this playlist to make sure this is the right spot for you. I'll have the link. The link is in the description. Okay, so we've talked about friction a little bit, and we mentioned drag, and both of these are forces that always oppose motion. Friction is when we're sliding across or two surfaces come in contact, and drag is when we're moving through some kind of fluid. Okay, so we had learned that there is a static friction and a kinetic friction. The static friction is the friction when the object is not moving, when one object is not moving relative to the other across that surface. And then the kinetic friction is when it is moving. And static friction is always a little bit stronger than kinetic friction because in the static case, the surfaces can kind of nestle together better than when they're sliding across the top of each other. Now, it turns out that the magnitude of the friction, so not the vector here, but just the magnitude of the friction, is proportional to the normal force. So the harder the surfaces are squeezed together because of that normal force. So my shoes are against the floor, that's pushing down with my weight, and then the floor is pushing up with equal but opposite normal force. That is giving me the friction between my shoes and the floor. But there's another factor. Do I have shoes with rubber bottoms or do I have shoes with more leathery bottoms? And that changes what's called the coefficient of friction. And this is true for both kinetic friction and static friction. The coefficient of kinetic friction is, or of static friction, is always a little bit bigger than the coefficient for kinetic friction. So that's where that difference lies. Now notice here we have a max here. This is telling us what's the maximum frictional force before slippage happens. So I'm standing here with my shoes. There's good friction, good coefficient of friction between my shoes and my wooden floor here, but I'm not really applying any of that. That never has to come into bear because I'm not moving anywhere. I'm not trying to move anywhere. So static friction, you're not moving, but I'm not opposing any kind of motion. Now, if I was on a slant and I was standing there, then I would want to slide down, and so friction would oppose that and keep me standing still. And so if I was on a slant and it kept getting bigger and bigger, eventually the downward force from my weight would outcompete the maximum, or would exceed the maximum frictional force, and then I would start sliding down the ramp. So this is always dealing with the maximal force. The kinetic friction, that's always going to be the same, and it's always going to be opposing motion, no matter how fast that we're going. Okay, let's look at an example here. Let's push a 25 kilogram box across the floor. So we're going to push this across the floor in this direction. We'll push it at constant velocity. So we're undergoing kinetic. We need to think about kinetic friction. And then let's think about the force that we need to apply. So if we draw the free body diagram for this, there is a normal force and a weight force, and those two are going to exactly cancel each other. And then I'm trying to push this way, so I'm applying a force, and then this is going to be a frictional force opposing that motion. This is going to be a kinetic friction. And I must be applying just the right force to keep this moving at constant velocity. If I start pushing with more force, there's nothing more this kinetic friction can do. It will become overwhelmed and I will begin to accelerate. If I push with less force, then the coefficient of friction will win out, will come to a stop, and then the kinetic friction will apply and it'll just hold me there. Okay. So let's just give some values. Let's say the coefficient of kinetic friction is 0.2, and we already know we're pushing a 20 kilogram box. So the normal force is just mg, and then we multiply by the coefficient to give us 49 newtons here. So I need to supply 49 newtons of force to move at constant velocity. If I apply more than that, we'll accelerate. If I apply less to that, we'll come to a stop. We'll decelerate. Okay. Let's get to this ramp situation that I mentioned earlier. If I'm standing on this ramp, or if you're standing on the ramp, and we're just going to raise this ramp right now to 27 degrees. We're going to say we're standing still there, and we're going to say that this is the maximum angle. If we go to 27.0001, we start to slide. Okay, so here's our max angle. Let's calculate our normal force now. Remember, we talked about this last time. The normal force is perpendicular to the surface. And we had the formula last time that this is mg cosine of this angle. And so we can plug in our numbers here and calculate 698 newtons of force. Now the weight, should have newtons here, the weight is mass times gravity, and the weight force, the magnitude of the weight force is 784 directed downward. Now because of this ramp, these are the free body diagram here, looks like this, which would initiate an acceleration down the ramp. But I'm not accelerating, I'm sitting still because I have just enough frictional force. This is normal, this is weight, and now I have just enough frictional force to oppose that acceleration. And we did this problem last lecture. And so what are we looking at here? We're looking at the tangent vector of the force in this direction. And so that is this, there's a component of the weight force that wants to push us down the hill. And let's see what that is. Well, it's going to be sine of that angle. And again, we talked about this last time, so you could go back and refresh yourself on that video if you're forgetting that. So that's going to be minus 356 newtons. If I now look at the frictional force, that's got to oppose that. So it's got to be opposite. It's got to be pointing up the hill. And so, or in positive x prime direction. So we're looking at a plus 356 newtons, or 356 newtons up the ramp. Okay. Now we said that any steeper we start to slip. So let's figure out the coefficient of static friction here. Well, we know the max frictional force is 356. And so if we simply take F max equals mu kinetic times the normal, then if we divide by the normal, then we get 356 divided by the normal force, which is 698. And so we get 0.5 as our static friction, coefficient of static friction. Okay, that's frictional force. It involves two contact between surfaces, and it always opposes motion. We mentioned another force a while ago now, drag force. Also opposes motion. In a sense, it's kind of a frictional force, but it really is important to think about it differently, because now what we're doing is we are moving through a fluid. So we don't have hard surfaces that we're talking about here. We're moving, say, through a fluid. So we can imagine this ball moving through a fluid. Fluid could be air. Fluid could be liquid. So by fluid, we mean either liquid or gas. And we have two components that make up the resistance to motion. One is called viscous drag. And if we kind of envision here, this ball has to find its way through so-called lamina of fluid. So the fluid has to flow around the ball as the ball moves through the solution. And there's a resistance to that called viscosity, a resistance to having layers of fluid flow at different rates around the ball. That's called viscosity. And so this is a viscous component to the drag. Notice it depends on how fast we're moving. So if we're just sitting still, fluid's not flowing by. But if we are moving through fast, then we have a larger resistance to that. This L is just kind of a generic holder for shape. So different shaped objects, of course, will capture the fluid differently. So a ball would move differently than a cube, than a person, but we kind of collectively just say there's some sort of effective shape. So you can think of that as if we had a cube or a person, what kind of shape, if it were made into a sphere, what would that sphere look like? And that's what this L is. Okay, now we also have inertial friction, inertial drag. And this happens because the ball, as it's moving, pushes together molecules in front of it compared to behind it. So it causes this difference effectively a difference in pressure. More molecules are hitting this side than this side, so that's going to resist motion. It would be like just running through where people are throwing maybe some lightweight beanbags at you or something. It just slows you down a little bit, but it slows you down because it's hitting you in the front more than the back. This too depends on velocity, but now it depends on velocity squared. So there's to the first power for viscous drag and to the second power for inertial drag. And we have density. And that makes sense because the more molecules per unit area we're trying to push through, the more we should see the inertial drag. And then again, this shape factor. Could be a sphere, could be something else. Now, this is in the area of what's called fluid mechanics. Very complicated, can get very complicated very quickly. One of the parameters that is really important in that is something called the Reynolds number. And the Reynolds number is simply the ratio of the inertial component compared to the viscous component. So if the inertial component is most important, as it is in air, like moving through air, then we can say, okay, in the limit, we're sort of dominated by the denominator here, or by the numerator. And if the viscous is much bigger, then we are dominated by the denominator. So we're going to look at sort of two limits there. We won't be able to really deal with this in great detail. There's a whole, if you become an engineer, you'll take a whole course on fluid mechanics. Okay, so in the high Reynolds number limit, that means the inertial is dominating, and the drag, okay, the drag is not the Reynolds number, but the drag has this form when we're at high Reynolds number. Okay, so the limit of high Reynolds number, the drag has this form. So this is called the coefficient of drag. And that's going to roll together things like the nature of the fluid that you're moving through. Density. This is density. And then this is the area of the object that's presenting itself to the fluid. And then finally, the velocity squared. Velocity squared. So, and I mentioned this occurs when we're moving through air. So that's why the faster you go on your bicycle, the harder and harder it is to ultimately pedal, because you're fighting the speed squared. So as you pick up speed, you face more and more drag resistance to your motion. Now, a really important thing to consider is something called the terminal velocity. So there, at some point, as much power you have in your bicycle, you're going to reach a maximum speed. Another place we think about this is if we jump out of an airplane and we're falling through the air. Eventually, we will reach what's called terminal velocity. That's where we no longer accelerate. We just reach the highest velocity that we would have, and if we fall any further than that, we're just falling at that same velocity. So if you jump out of an airplane, you'll speed up for a while, and then you'll just move at a constant velocity. So you'll end up going in uniform motion, which means the net force is 0. So this allows us to calculate this, and I kind of overwrote my free body diagram. You initially jump out of an airplane, you're all weight. You start to move a little, you develop some drag, just a little bit. But then you reach terminal velocity. That's when the drag plus the weight equals 0. So your drag is equal and opposite to the weight. So let's take our drag formula and set it equal to mg. So here's our weight term, and here's our drag term, and then we'll label that as a special velocity. That's the terminal velocity. Then we'll just simply solve this algebraically for terminal velocity. And so this is an equation for terminal velocity. All right, so that's moving where the inertial is dominating, so like objects moving through air. Objects moving through water, for example, that's where viscous is dominating, and in the limit of low Reynolds number, the drag is given by just a constant that represents the shape. It's related to L, but a little bit different. Still represents the volume. Then the viscosity. So this is viscosity, and that just depends on the fluid. So it doesn't depend on the shape that's moving through it. It depends on the fluid. So water has a certain viscosity at a certain temperature. Ethanol has viscosity at a certain temperature as well. If this is a sphere, then it turns out that I said volume. It's just representing a size, basically in a scaled radius of a sphere. And for a sphere, it turns out it's 6 pi r. And so this is, if we plug that in for this limit here, we get something called Stokes' law. And Stokes' law shows how a ball or a sphere moving through a low Reynolds number fluid will behave. And maybe you can pause the video now and set this equal to mg and determine the terminal velocity in the low Reynolds number limit. Just want to point out again, I've said it twice here now, but the viscous component, so low Reynolds number, dominated by this velocity to the first power. So you don't pay as much of a penalty for going faster in the low Reynolds number. Here, velocity to the second power, or velocity squared, or speed squared, you're paying more of a penalty. Okay. All right, so again, this is about all we're going to see with this. Couple of problems in the homework set. So like I say, this gets complicated really quickly, and there's whole courses on it, of course.